Okay, hello. This is Michael Blonsky,
I'm Alex Dobbs.
And I'm Hazen Goodyear.
and we are presenting the EENG 581 final project on optimal operation of an islanded microgrid. So here's our table of contents. I'll start going over the problem definition and talk about the first method that we are going to present, which is on convex optimization. And then we'll talk about the second method, which was looking at more of a heuristic analysis. So first, just the problem that we're trying to solve, we were given a microgrid layout with a certain number of DG units, energy storage units, and loads. And we were told that this microgrid was islanded due to a natural disaster. So the first thing that we did, we looked at all of the data and we organized the microgrid into 8 different nodes based on where each of the circuit breakers were. So we were also told that the main thing that we can control the generation of each of the DG units and the battery devices, and then also the switches, whether to turn all of the circuit breakers on or off. So we determined that there were 8 nodes and that we could essentially turn each of these nodes on and off depending on their location in the microgrid. And here's just a diagram showing where those 8 nodes are, and then a brief summary of what each of the loads are within those nodes. So for both of the methods, we had a few assumptions. So we just want to be explicit about all of those. So we assumed no I2R losses in the network. We assumed no backup generation or demand response capability from any of the customers. We determined a weight for each of the loads based on the load type, which were given in the problem statement, and determined the criticality of each load based on that. We are using hourly intervals in our analysis and not looking at any shorter intervals, so not looking at spinning reserves or flexibility on the seconds or minutes time scale. And finally, we were given forecasted loads, and we assumed that the actual loads that would happen during the day would be exactly equal to the forecasted loads. Okay, so now I will talk about method 1, convex optimization, and I'll go through the formulation and how we solved it. For the formulation, we had a set of parameters, variables, and then the objective function and the constraints. So these are all the parameters. We have cost parameters, cost of the generation, cost of lost loads. So anytime that a load is disconnected, we have an associated cost with that. And then cost of using the battery. We also were given maximum power output of the generators for each of the generators given, and that also varied with time. The power of the loads themselves, which either had to be on or off. Maximum storage for the battery, initial charge of the battery, a Boolean matrix. This was really just created based on the design of the microgrid. So which of the 8 nodes are connected to each other. And then finally, F max is a maximum flow between any of the 2 nodes, which we assumed to be infinite because there was none given. So I believe all of these were given, at least implicitly. Some of them we derived, except for the lost load cost, and I'll talk about that more in a little bit. Here's a list of all of the variables in the optimization problem. So we have the actual power of each of the generators, the power of each of the batteries, the battery charge as a function of time for each battery, and then 2 Boolean variables, N and M, that correspond to whether or not a node is on at a given time, or a node is connected at a given time. And then F is the power flow between each of the nodes, and that's also a matrix for each time. And this is our objective function for the optimization problem. So the objective was to minimize all of the costs, the generation costs and battery costs, which were given, and then we converted the lost load penalty into a monetary value, a cost, using the cost function. I'll note that this objective function is mostly linear. The first two terms are linear, and the last term is nonlinear, but could easily become linear by adding a few extra variables. So that is something that that the optimization program did on the back end. But this did end up being a mixed integer linear program. So each of these constraints are also they're convex and they're also linear. So I'll go through these quickly. The first two are just power conservation. So power conservation for each of the 8 nodes, and then also for each of the battery systems. We also have a relationship for determining whether the node is on or off. A bunch of constraints based on maximum amounts. So maximum flow, maximum generation for each of the generators, and then maximum charge of the battery. And then the last few constraints just say that the flows between two nodes have to be equal and opposite. So the flow from node 1 to node 2 should be opposite the flow from node 2 to node 1. The node connections should be symmetric. So if 1 and 2 are both connected, then 2 and 1 are also connected. And then finally, power generation and battery charge are always positive. So going back to the lost load cost, these are the actual numbers that we decided on for the 2 scenarios for this method. The first scenario has relatively low lost load costs, around $200 per megawatt hour and up. We decided that the lowest cost would be for residential loads, the highest cost for emergency loads, which were the fire station and hospital, and then everything else was somewhere in between. I'll note that all of these lost load costs are higher than all of the generation costs. So those were all on the order of $90 or $80 per megawatt hour. So we are incentivizing the system to use that generation so that you're not losing loads. And then in the second scenario, each of those costs were doubled to see what impact that would have on each on the optimal value.
So here's some of the results for the first method. You can see the 2 scenarios here and the cost for each scenario. Overall, scenario 1 was a cheaper cost. That's partially due to the higher penalty for lost loads, and this causes the batteries to be used more than once. So we have to incur the cost of recharging the batteries and having the batteries go through another cycle. Although scenario 2 actually only increases the overall cost by about $90. Here's the generation and demand for each scenario. The higher lost load penalty in scenario 2 causes a greater amount of the demand to be supplied. I think from this table, the most important or most informative row is the last row, where you can see 94% of demand was supplied in scenario 1 versus 94.9% in scenario 2. So by increasing the lost load penalty, we were able to supply an additional percent of the demand that was required or requested. Here we have which nodes are lost throughout the day. You'll notice that in the middle of the day, we are actually able to supply all the power, which you'll be able to see later on as well in some graphs. When we did have to lose a load, these are the loads that were shed. At 7 and 8 a.m., we lost the same nodes, 1 and 3, between the 2 scenarios. But at 4 p.m., due to the recharging the batteries and the higher lost load penalty, we had a little bit more supply available to us in scenario 2, so nodes 3 and 8 were turned off, and we were able to supply a little bit more demand in that time slot. These two plots show the generation for each scenario for each DG unit. They're very similar. What you want to note here is that in scenario 2, counterintuitively, it looks like the fuel cell gets turned off. That's because it's connected to a node that has only one load on it, and the load requirement of that load is a factory, and it requires more generation than the fuel cell can supply. So when we have the extra reserves with the battery, it actually makes sense to turn that load off and disconnect that generation unit completely to supply more load elsewhere. This plot shows the state of the battery charge over the entire day. You can see in scenario 1 that the two batteries are used in the morning to supply load, but then are not recharged throughout the day, so their charge goes to 0 and stays at 0. In the second scenario, where we put a higher lost load penalty, the extra generation that's available in the middle of the day is actually used to recharge the batteries so that they can be discharged again when the load will be greater at night. And here we have the total demand given by the problem statement and the supplied demand of each scenario. You can see in the morning, each scenario has a little bit of load shedding between 7 a.m. and 9 a.m. It's the same amount between each scenario. And then throughout the middle of the day, the demand is being met by the supply up until 4 p.m. In scenario 1, for the last couple of hours, there's load shedding at a greater amount than in scenario 2. Scenario 2 is able to supply a little bit more load between 4 and 5 p.m. because the batteries have been recharged.
Optimization software and the approach such as the one we used in method 1 become necessary when dealing with very large and complex electrical networks, especially as the number of loads and energy sources increase. For this problem, however, containing just 8 nodes and 6 power sources, a manual analysis of the system can serve as a valid approach to solving the problem. So in method 2, we use a heuristic approach mainly to solve the power mismatch problem, which we'll talk about in a moment. We'd like to consider an energy network, a grid with limited data and technology, where this natural disaster happens. It's 6 a.m. and an operator has limited data and must make a real-time decision in the next hour as to how to approach the following 12 hours. So that analysis might likely include some qualitative reasoning as well as just some societal considerations that a computer program might not be able to identify. So based on the given data, each hour between 7 a.m. and 7 p.m. can be identified as a period where either dispatchable supply is either greater than or less than the forecasted demand. In this table, we see a breakdown by hour of the total load of the system at every hour, or the total forecasted demands, as well as the available generation per hour. And note, this generation does not include battery resources. And then the final row, delta, shows the difference, therefore the power mismatch, the deficit between supply and demand. So this problem can be broken up into 2 tasks. The goal is to shed loads and minimize loss of loads for the red hours, which appear in the morning, as well as the final 3 hours. And then during the blue deltas, we want to minimize the operating costs. We'll be able to meet all demands, but we want to do it in an economic fashion. And this heuristic method is going to address solely the power mismatch problem, therefore the hours between 7 to 9 a.m. and 4 to 7 p.m. Without yet using the weight costs, a visual inspection of figure 1 of the electrical network can provide some heuristics about which nodes are acceptable to island. So we have these 8 nodes. Node 1 has 3 residential loads. Yes, we could island these loads. They'll lose power, but there's nothing too critical here. Node 2, it has 2 loads that aren't highly critical. However, it has the largest generator in the network. And if we island this node, then the whole network will lose more than half the available generation. Node 3, it's a school. We would ideally not like to island the school. If we turn the school off, for example, residential loads might increase dramatically in the real world, as well as there might be economic harms to businesses and factories as parents perhaps leave work early to go home to be guardians for the children. Node 4, most important, it has a fire station, which is a critical load. We cannot really island this node. Similarly, for node 5, it has the hospital. It does have some DG. It has DG2 unit on it, but that unit is not enough to power all those loads. And then loads 6 and 7 are loads that we could potentially, but not ideally, island. And then load 8 is a factory, and it has its own fuel cell. However, the fuel cell supplies 50 kilowatts, too little energy, too little power to be able to power the factory by itself. So we've constructed this table using the heuristics of which nodes are acceptable to island, as well as our MATLAB analysis of the system constraints during the 2 periods of undersupply, of where supply is too less than demand. You can see for the morning hours of 7 a.m. to 9 a.m., there's a total power deficit of 1.05 megawatts over the course of those 2 hours. So we will attempt to solve this deficit by losing as little load as possible. So disconnecting nodes 3 and 8 initially appears as the best way to shed enough load so that supply can meet demand with shedding as little load as possible. So doing this would get rid of 1.15 megawatts, which is only 100 kilowatts more than necessary, which is quite ideal, at a societal cost of $345 per hour. Doing this, however, would also disconnect the fuel cell at node 8, reducing the overall generation in the network and leaving a new deficit of 700 kilowatts, even after nodes 3 and 8 are disconnected. So at this point, you'd have to disconnect another load. Node 7 is the lowest value, and now if you disconnected all 3 of these nodes, supply would be able to meet demand, and you would have lost 2.45 megawatts at a cost of $605. So this option is not ideal. So instead of disconnecting nodes 3 and 8, disconnecting node 7 appears to be the next best solution, where you would lose 1.3 megawatts, only 250 kilowatts more than necessary, and that would be at a societal cost of $260 per hour. However, again, if you disconnect node 7, it necessarily islands node 8, where the fuel cell is simply not enough to power the factory. Therefore, both nodes would need to be disconnected for a total loss of load of 2.15 megawatts and a societal cost of $515. So the third option turns out to be the solution, and it is disconnecting node 7. Loss of load 1.7 megawatts, only 650 kilowatts more than necessary. At this point, that is the least value, going over the supply-demand mismatch of 1.05 megawatts, and this would be a societal cost of $340 per hour. So node 1 is disconnected right at 7 a.m. and the now excess of 650 kilowatts of generation will be used during that hour to charge the nearly empty batteries during the 7 to 8 a.m. hour. Then at the start of the 8 a.m. hour, the new battery storage available is 850 kilowatts. And this reduces or improves the supply-demand mismatch from 1.05 megawatts to 0.2 megawatts. And if we only need to shed 200 kilowatts now, the best solution is to disconnect node 3 for the final hour. So at 7 a.m., node 1 is disconnected, and the excess energy charges the battery. At 8 a.m., node 1 is reconnected and node 3 is disconnected between 8 and 9. The method is then used to solve the power mismatch problem between the hours of 4 to 7 p.m., where the supply-demand mismatch is now 1.75 megawatts. So looking at these 5 acceptable nodes to islands, it would appear that if you shed node 3 and node 7, you would be shedding 1.76 megawatts, which is enough and only 10 kilowatts more than you would need to shed to solve the problem. However, once again, if you shed node 7, then you're detaching node 8 as well, and that adds up to much more load being lost. So then the next lowest load to shed to reach at least 1.75 megawatts becomes node 1. However, there's another option during the afternoon now that the batteries are fully charged, and that is that you can shed node 8 for an hour, and then the supply-demand mismatch becomes 750 kilowatts, and you would then use half of the battery storage, half of the 1.5 megawatt hours of battery storage to make up the remaining deficit for that hour, and then you would be able to do that for one more hour. So the final solution to the afternoon, using the heuristic analysis, also allows an operator to decide that perhaps it would be more important to be able to provide power to the residential loads on node 1 between the hours of 5 to 7, when it's more likely that people are home, it's getting dark outside, and they're cooking dinner. So if node 1 only needs to be disconnected for 1 hour, it's more optimal to do that starting at 4 o'clock. And on the table on the right, you see the heuristic analysis solution to shedding loads throughout the day. Where in the afternoon, node 1 is shed for the first hour, and then the second 2 hours, the factory on node 8 is disconnected, and the battery energy is split evenly over those hours to make up the remaining deficit. Here are just 2 plots. In the top, we see the original demand for all 8 nodes during the various periods of undersupply. And then the plot on the bottom looks quite similar, but each period is missing one load. It's missing the load that needs to be shed. So in the first group, from 7 to 8, load 1 doesn't exist. The next group, node 3 doesn't exist. The next group, node 1 is again disconnected, and then for the final 2 hours, load 8 is disconnected. Wrapping up, the 2 scenarios used in method 1 varied by the lost load costs that were assigned to the various loads in the setup of the problem. The result between these 2 scenarios were quite similar in many ways. The percentage of supplied demand only differed by 0.9% between the 2 scenarios, and the percent difference in the total costs seen in the last row on this table, they only differed by 0.7%. The higher associated load costs in scenario 2 allowed the system to run more expensive actions like charging and discharging the batteries. This led to the main difference between the scenarios, such that in scenario 2, the batteries were able to supply the extra energy needed to power node 1, which had a greater demand than nodes 3 and 8, allowing it to stay connected for 1 hour in the afternoon. The heuristic analysis led to the same load shedding solution for the morning hours as was found in method 1, and similarly used the batteries to allow node 1 to stay connected for at least 1 hour during the afternoon. This method, however, differed in that it only disconnected node 1 from 4 to 5 p.m. when households might realistically be less dependent on electricity than they would in the 2 following hours. And then for the final 2 hours, it disconnected the factory on node 8 and used the battery energy storage to perfectly meet the remaining supply and demand mismatch. So in conclusion, we found that the higher lost load costs resulted in fewer lost loads with more expensive operation costs. Implementing the human decision making in method 2 introduced a practical solution that the computer program in method 1 did not. And this demonstrates that this method would be handy in the real world when a operator has little time to come up with a solution and perhaps not the technology or software to fully optimize the solution. We also found that the results could vary largely based on what assumptions are made. We made some simplifying assumptions, such as that the circuit breakers could only be switched on hourly intervals. This problem could be made much more complex and computationally intensive if instead we decided that the circuit breakers could be changed on a minute resolution. However, some of the assumptions that we made also kept the problem challenging, such as the assumption that this occurred on a school day and we couldn't shut down the school, as well as the assumption that no loads, including the hospital, had backup generation. And this kept the supply-demand mismatch to be as large as possible. And then the final large consequential factor are the load costs that we assign to loads. We aggregated all the load types into 3 loads. They are the critical loads, residential loads, and the others were all grouped into one type. However, we could have given different weights to all of those unique 8 load types. As well, we could have changed those weights dynamically throughout the day to reflect, for example, that residential loads necessarily need power in the morning when people are waking up and getting ready to go for work, and then maybe the weight for residential loads could be slightly less in the middle of the day when people are more likely to be at work. And that concludes this presentation. Thank you.